SwayamPrabha. Digital India. Educated India.
With this lecture, we begin the week 6 of the course, and in this week we will spend time on statistical thermodynamics or microscopic thermodynamics. The contents of this week 6 are basics of statistical thermodynamics or microscopic thermodynamics, excitation of various molecular energy modes, macrostates and microstates, and finally, using all these concepts together to understand equilibrium composition of high temperature air. To begin with, we look at classical thermodynamics and how it contrasts with statistical thermodynamics or microscopic thermodynamics. And we recall that classical thermodynamics basically expresses different thermodynamic variables in terms of any other two thermodynamic variables. So, that is basically the equilibrium thermodynamics we all are aware of in the classical thermodynamics domain. However, absolute values of thermodynamic variables are not derivable by this process. While when we look at the microscopic behavior of the thermodynamic system comprising of a large number of gas molecules and atoms, we see that obtaining absolute values of thermodynamic properties is indeed possible and possible from first principles. So, that is one of the prime utilities of statistical thermodynamics. We also get deeper into the molecular picture of the thermodynamic system, and thereby we try to understand the different energy modes, and this becomes very relevant in the context of hypersonic and hypervelocity flows, where the flow gets heated up due to the viscous dissipation that occurs in the boundary layer and high shear regions of the flow, as well as due to very strong shocks which are formed on such vehicles. And therefore, we need to understand that what are the different forms of energy existing in the molecules and how do they get excited, over what range of temperatures do those changes occur. And we got a glimpse of that in some of the lectures of week 5 already. So, let us get deeper into the microscopic picture. We begin our discussion with modes of molecular energy, and here by the word molecular we do not only confine it to molecules alone, we also mean atoms. So, it could be either molecules or atoms, or it could be a mixture containing both. But here of course, we mostly confine our discussion to single species gases. Now, when we talk about the different molecular energy modes, we begin with translational energy. We choose to use this nomenclature, the epsilon, with a dash and a subscript, which over here is translational, and we write it of course in an abbreviated form, trans. There would be other modes adding on, where we mainly would be talking about a change here in this block. And translational energy is possessed by both atoms and molecules. Here is a small sketch trying to represent what we mean. So, in a 3-dimensional Cartesian space, we have 3 components of velocity possible when an atom or a molecule is translating. So, here we have an atom with a velocity V a vector, which would have its respective components along x, y, z directions. Similarly, you have a diatomic molecule here. You can see the atoms here with a bond in between, and that also has a velocity. Here it is V m M stands for molecule, and this is an instantaneous picture, because the velocity is a function of space and time. So, if we look at it at a different time instant, the velocities will be altered by them. Now, the translational kinetic energy of the center of mass of a molecule or of an atom is represented by this term. Since translational velocity has 3 components, as we have already seen, therefore, the atom or molecule has 3 geometric degrees of freedom in translation. Associated with this is also thermal degrees of freedom, and we need to understand why that happens. Since kinetic energy has an inherent connection with the thermal energy of a gas particle, and we will be showing in due course that this epsilon expression for translational energy is connected with the 3/2 R T, where T is the absolute temperature of the gas, R is the specific gas constant. We notice a difference in nomenclature here, that we are not writing it as epsilon dash translational, but rather as epsilon alone. We will discuss that later, but the point we are trying to make over here is the connection between kinetic energy and thermal energy, and if you consider T as a measure of that, then definitely this expression is enough for us to realize that yes, kinetic energy and thermal energy are indeed very closely connected when it comes to motion of a gas particle. And because of the velocity components that the gas particle has in the 3-dimensional space, there are 3 geometric degrees of freedom. Correspondingly, there are also 3 thermal degrees of freedom. There is another form of energy which is common to both atoms and molecules, that is the electronic energy, for which, as I said earlier, we will see a change in the subscript here. So, we choose to represent that as lowercase e l, and with a sketch we can represent that well. Around the nucleus of an atom or a molecule, you would have the orbiting electrons, and there would be several electron orbits over which the electrons would be moving around the nucleus, but of course, that forms more of a cloud rather than very discrete ones that we have represented here, because this is just a kind of simplified representation that we are going for, and the nucleus of course contains the protons and the neutrons. And what kind of energy are we talking about over here? In terms of a molecular energy mode, we are talking about kinetic energy of the electrons as they orbit around the nucleus, as well as the potential energy of the electrons as they maintain their orbits. So, that comprises the electronic energy which the atoms and the molecules can have. There are some other energy modes which are specific to molecules alone, and they do not contribute to the atoms energy. So, they are essentially rotational to begin with, and there is another form which comes in the next slide, that is the vibrational. So, we will come back to vibrational a little later, but for now we will spend a few minutes on rotational. So, here in this figure, for example, on a larger scale you can see that well, there is a diatomic molecule comprising of the 2 atoms that you see over here, and the bond is like a straight line connecting the 2, and the 2 atoms along with the bond are aligned along the ZZ bar direction. So, that is the instantaneous orientation of the molecule. And if you imagine that they can be rotating about some axis, then if they are rotating about the ZZ dash axis, that is where the rotational energy will be negligibly small, because the rotational energy basically depends on 2 factors which are mentioned over here. One is the rotational velocity, you can say omega, the other is the moment of inertia, let us say I. And if there is a non-zero omega, there is a non-zero I or a reasonably large I, then we are talking about a reasonably large rotational energy. And about the axis z z dash with the current orientation, the I would be very small. So, even if the omega is reasonably large, it would end up having very small rotational energy. While if it was rotating about the x x dash axis, like the way we have shown over here, or if it is rotating about the y y dash axis, then you can imagine that it will have significantly large moment of inertia about those two axes, and therefore, there would be significant rotational energy. So, diatomic molecules therefore, though they can have 3 geometric degrees of freedom ideally in rotational motion, but as you can see over here, in one case, since the rotational energy will be negligibly small, therefore, we would confine it to 2 geometric and 2 thermal degrees of freedom. And there are molecules where you could imagine that the bonds are not linear. For example, you can have a molecule looking like this, and that is precisely the case over here when it is H2O. And then you can imagine that if they are rotating, whichever axis they choose to rotate about all the axes that we have shown over here in the Cartesian x y z plane, about all the axes, there will be non-zero and reasonably large rotational energy, and therefore, there will be 3 geometric and 3 thermal degrees of freedom involved in such cases. So, non-linear molecules are of course different compared to the diatomic kind that we discussed earlier. Diatomic will be typically, let us say, like O2, N2, etc. There are also linear polynomic molecules like CO2, where the bonds are all aligned, collinear, in which case the behavior is very similar to the diatomic molecules. So, this is a little bit about the rotational energy, and this is typical of molecules, it does not exist for atoms. When it comes to the last form, the vibrational energy, then again we see a change in the subscript. Again, we forgot to mention that we saw a subscript here too. When it is rotational, we will represent it as ROT, while for vibrational it is VIB. So, we are going to follow this simplified nomenclature in the upcoming lectures. When we study the vibrating energy of a molecule, here it is a diatomic kind that we are showing, we can imagine it as a spring mass system. Of course, there are 2 lumped masses at the end, and there is a spring in between, and the interatomic forces are represented by a spring, and there is a mean intermediate or rather interatomic distance separating the 2 atoms, but when the atom has vibrational energy, then when the molecule has vibrational energy, then the atoms would be vibrating about the mean position, and therefore, they may at times come closer, like the way these arrows are showing, or they may move further apart, but they tend to oscillate about a mean interatomic distance. And the vibrational energy, it arises due to the following forms of energy which lie embedded, that is the kinetic energy of the linear motion of the 2 atoms as they vibrate back and forth about their mean position. So, it is like kinetic energy of the translating masses if you look at its macroscopic mechanical counterpart, and also the potential energy of the molecule by virtue of the intermolecular force, which is like potential energy of the spring in a spring mass system. Now, because of the 2 kinds of energy constituting the epsilon dash vibrational, there are 2 thermal degrees of freedom. So, with that we get a glimpse of the different forms of energies which may lie in an atom or a molecule, and we find that for atoms it is only the translational and electronic kind which will contribute, while for molecules it will be translational, electronic as well as rotational and vibrational, which are the additional forms compared to atoms. And each one of the above forms or modes of energy can exist only at certain discrete values. They cannot just vary continuously, and therefore, they are said to be quantized. Whichever mode of energy that you look at, they have this quantization in their behavior. That means you can jump from one discrete level to another, you cannot lie in between. And that is what is kind of represented through this diagram, where we try to put all the energy modes that we discussed in a common diagram, in a common sketch, and it gives you some idea about the discrete energy modes that we are talking about. So, these are the quantized energy levels which are given from quantum mechanics. We are not going to delve into that in deep, but we will sometimes refer to some of the results which are available from the theories. And we have of course mentioned that we recall for atoms its translational and electronic alone. For molecules it is the 4 forms that we are talking about, and therefore, to keep it general we have shown the 4 pillars which is applicable for molecules. You see that the translational energy, the discrete levels are very, very closely spaced. It begins with a lowermost possible level which is marked as epsilon 0 dash trans. So, that is like a ground level, a ground state if you call it. And then if you move to the next discrete level, it becomes epsilon 1 dash trans. Similar is the case for the other energy modes, that they have a ground level of energy followed by the first one and so on. The very close spacing of the translational is not what happens in rotational. You see wider jumps between discrete energy levels, and the jumps seem to increase as you go to the higher energy levels. In the vibrational case, it is the other way around. The first jump from the 0 to the 1 level seems to be the largest, followed by reducing levels of energy jumps as you move up. So, I give this arrow in the sense that the delta change that you need to move from one level to the other, that reduces as you go to the higher energy levels. Analogous is the case in electronic, where like vibrational the first jump is very large, while the subsequent ones get a little reduced. However, the first jump itself seems to be significantly larger even compared to the vibrational, and much more than the rotational, and much more than translational, and therefore, you can understand that large amount of energy changes are involved in order to excite an electronic energy mode from one level to another. So, the findings are kind of again summarized over here. We will go through them once more because they are very important. The spacing between the translational energy levels is very small, and that is why the translational energy level diagram looks almost continuous. So, if you go back to this diagram, this is essentially an energy level diagram. The spacings between rotational energy levels are much larger than that between translational energy levels. Further, the spacing between two adjacent levels increases as the energy level increases. So, one thing is that it is much larger than translational, the other is that the spacings would increase as the energy level increases. Spacings between vibrational levels are much larger than between rotational energy levels, and adjacent vibrational energy levels become more closely spaced at higher energy levels. So, this is in contrast to what you have in the case of rotational. Closely spaced means basically we mean to say that the gap between adjacent levels decreases. The spacings between electronic energy levels are quite considerably larger than between vibrational energy levels, and it is similar in nature to vibrational energy levels in the sense that the difference between adjacent electronic energy levels would decrease at higher energy levels. So, we see the sketch once again to recall these facts. Now, we talked about the lowest allowable energies, which we marked as the zeros, epsilon zeros, and these levels are defined as the ground state for a gas molecule. So, ground energy state, that is what we need to remember. They correspond to the energy that the molecule would have if the gas were theoretically at a temperature of absolute 0. So, if you were to take the gas to 0 Kelvin, then these are the energies which would exist in the different modes. This is why these are called as 0 point energies for translational, rotational, vibrational and electronic modes respectively. Incidentally, the rotational 0 point energy is exactly 0, while these, none of these are equal to 0. That means, even if you were to take it to absolute 0, if you were to take the molecule to absolute 0, it would not have 0 values of the translational, vibrational or electronic ground states, while the rotational energy will go to 0. The energies could be more conveniently measured about the 0 point energy values. They are expressed using these following expressions. So, if you were to take the epsilon dash expressions for translational, rotational, vibrational or electronic and then subtract the ground state energies, then you end up getting the epsilon expressions without the dashes. And you may recall that in one of the previous expressions where we were talking about the connection between kinetic energy and thermal energy, we had used an epsilon expression without a dash. So, now you can figure out what we were trying to mean between the difference in nomenclature that we were seeing over there, one epsilon with a dash, the other without a dash. And here, because you have exactly 0 value for the ground state for the rotational mode, we therefore have not subtracted any value there. Now, if you were to express the epsilon dash for the molecule in general, it would comprise of the epsilon values without dash plus the complete expression for the epsilon 0 dash, which we have over here. Now, this portion all are measured above the 0 point energy, thus all are equal to 0 at T equal to 0 Kelvin. So, if you were to evaluate this portion, this is precisely 0 when you are setting the temperature to 0 Kelvin. Now, this portion is the 0 point energy and it is a fixed quantity for a defined gas molecule. So, epsilon dash is the sum of individually quantized energy levels comprising of the different energy modes. Therefore, epsilon dash is also quantized. Since the entities which make up epsilon dash are quantized, therefore, epsilon dash itself will also be quantized. So, this is an important concept which we will be needing very soon. Just like individual mode wise energy level diagrams can be constructed for a given molecular species, the allowable total energies can also be represented in a separate energy level diagram. So, we can have energy level diagram for epsilon dash like we had for the individual energy modes. And how will that be formed? It will be basically formed by combining the contributions coming from translational, rotational, vibrational and electronic, and therefore, there will be a separate quantized energy level diagram representing epsilon dash. In addition to energy level, one needs to define energy state. In quantum mechanics, molecules are not only identified based on energy level, which is the epsilon dash that we are talking about, but also through angular momentum. The angular momentum has an associated direction since it is a vector. Quantum mechanics establishes that molecular angular momentum orientation is also quantized. This is a very important finding from quantum mechanics, which means that if you have a diatomic molecule, then you may have a omega vector pointing this way, another omega vector pointing this way, and there are such finite number of angular momentum vectors that you can talk about, which are all quantized forms. There may not be any vectors lying in between if you do not have any allowable quantized levels which can bridge the gap between these vectors. So, that is precisely what we mean by quantization of the angular momentum vector, and that is what comes from quantum mechanics. So, the rotational energy is identical, while the rotational momentum has different directions, and this is basically the background of defining energy states, not only energy levels, but energy states. Therefore, according to quantum mechanics, these are distinguishable energy states. So, one rotational energy giving to multiple rotational energy states, which are also quantized. Finally, the number of states that we are talking about over here, which may arise due to the rotational momentum that the molecule possesses in a quantized sense, is called as the degeneracy or statistical weight of the given level epsilon j dash, and is denoted by G j. So, you need to take care about the nomenclatures that we are introducing at this point. Let us consider a system consisting of a fixed number of molecules n, and let n j be the number of molecules in a given energy level epsilon j dash. So, on one hand, the instantaneous population distribution that you have spread over the different energy levels, the quantized energy levels, will give rise to the total number, the total population that you have. And on the other hand, the total energy of the system will be denoted by capital E, which will come from the individual contributions of each one of those quantized energy levels, weighted by the number of molecules that lie in that energy level. So, on one hand you have the number to be conserved, on the other, based on the number distribution or the population distribution or the macro state that we are talking about over here, you will have a corresponding energy, total energy of the system, which we are calling as capital E. And why is it that the state of the system may be changing from one point of time to the other? Because the molecules are in incessant state of collision. So, due to these incessant collisions, some molecules will change from one energy level to another in a quantized sense. Hence, when we look at our system at some later instant in time, there might be a difference in the Ng distribution or Nj distribution rather, and hence a different population distribution or macro state. So, remember that the population distribution is basically the distribution of Nj spread over the different j levels of energy, and that is what gives rise to a macro state. And we can later see that there would also be a concept of micro state, which we will gradually introduce. So, for a system of n molecules and energy E, let there be a series of quantized energy levels, as we have already defined, with corresponding statistical weights G naught, G 1, etc. And we will discuss about the statistical weights further. At a certain time instant, let the molecules be distributed over the energy levels with a certain population distribution. So, those are the Nj's we were talking about. This constitutes a specific macro state. In the very next time instant, because of molecular collisions, the populations of some levels can change without changing the total population. So, the n remains fixed, but the Nj distribution over j levels can change. This would lead to a different set of Nj and hence a different macro state. In this manner, over a period of time, one particular macro state, which implies one specific set of Nj, will occur much more frequently than any other distribution. This is called the most probable macro state, and it occurs when the system is in thermodynamic equilibrium. So, this is a very important concept. This is basically the underlying concept of thermodynamic equilibrium in statistical thermodynamics or microscopic thermodynamics. We repeat it again, that over a period of time, one particular macro state, which implies one specific set of Nj, will occur much more frequently than any other distribution, and this is called the most probable macro state, and it occurs when the system is in thermodynamic equilibrium. This definition is very, very important. Finally, we still do not know how this distribution will be there, how the Nj's are going to be distributed, and consequently what would be the energy. The problem basically reduces to finding the most probable macro state for a fixed number of identical particles n, with their energy consequently defined by this expression for E. And to solve the above problem, we need to define another parameter, which we call as microstate, which we will discuss. We will just talk about it in the beginning for a minute or so before we close this lecture. So, here we have reached a point where we can see the different energy levels, and then we are saying that the quantized total energies could have different statistical weights or degeneracy corresponding to the different energy levels. You remember why the degeneracy occurs. We discussed about the omega vector taking different quantized directions, and therefore, you can very well understand that this is one way of explaining the statistical weight or degeneracy. So, let us say at this energy level, the possible quantized states are 1, therefore, the G naught will be given by 1. Similarly, in the other energy states or levels, you would have other set of levels, and here you see that for epsilon 1 dash you have 3 energy states and so on. This way, the number of energy states that we have corresponding to a particular energy level will decide the degeneracy. We will discuss about it at length in the next lecture. So, let us conclude by saying that in this lecture we started discussing about the fundamentals of statistical thermodynamics. The different molecular energy modes were discussed. The concept of macro state was introduced. The discussion of microstate was initiated, and we will take it to greater detail in the next lecture. Thank you.